All right, let's get going on today's meeting. So today we are going to continue our look at sampling distributions and the distribution of sample means. So as we mentioned last time, we began this kind of new stage in our statistical understanding with the normal distribution part one, and then we moved on to the normal distribution part two. And now we're doing a sort of inception style stacking of distributions on top of each other. And we introduced that idea with sampling distributions part one. And today we are going to go and finish that last level with sampling distribution part two. So this is all building up to when we start our first real foray into inferential statistics, and we start to do hypothesis testing, which is where a lot of the strength of statistics lies in psychology. It allows us to ask questions and then use statistical analyses to remove any bias that we might have as humans in our minds, and just put it all into an algorithm that we can follow to make objective and intelligent decisions about whether basically a treatment works or whether a treatment doesn't work. And today we're going to see firsthand a little almost miracle that occurs that allows statistics to be the powerful tool that it is. So you might recall before that I said that this was not a course in mathematics. However, today we are going to witness a little of what I like to call mathe-magic, because it truly is an astounding phenomenon that we are able to take advantage of and build this entire idea of inferential statistics around this one universal miracle that occurs. I don't know how else to describe it. And it just is about as close to magic as I think we probably get in psychology. All right, and we're going to continue our ComRom because we are going to use what is probably my favorite online app in the Statlet repertoire today. And it's going to be something that allows us to take a look not just at sampling, but to actually visualize the idea of sampling distributions. So we're going to be taking a look at a whole bunch of samples, how they come from a population, how they stack up into a sampling distribution, and then how that sampling distribution is related back to the population and why that relationship is so incredibly useful. So today we are also going to have some of those do it with me demos where you can follow along and you can build your own sampling distribution so you can get a real feel for how these phenomenon are related to each other and what they actually are. Because again, we're going to be dealing with three distributions and it's really easy to get those confused. So hopefully after today, you'll have a more solid foundation of which distribution is which and which properties each one of those has. All right, so today is going to be all about sampling distributions. We are going to start off with a look at the words that do the work. There are a lot of new terms that are coming in, and we are going to take a look at the sampling distribution's relation to the population distribution. Specifically, how is it related to the population distribution mean and standard deviation? And then we're going to take a look at characteristics of that sampling distribution. For example, what is its mean? What is its standard deviation? And all of this depends upon its sample size. And then to finish it off, we're going to take a look at describing the shape of a sampling distribution of a sample mean. And this is where we bring in that mathe-magic of the Central Limit Theorem. And then we'll end the meeting today with a little, what I like to call null hypothesis teaser. So null hypotheses are a part of hypothesis testing. Once we get to them, we're not going to take a look at what they are today, but once we get to them, sometimes it's a little confusing in terms of why we need the null hypothesis. So I'm just going to give you a little teaser of what's coming up. And we're going to do that by talking about cars and boyfriends. All right, so to start off today, we are going to take a look at the words that do the work. So we are delving into a situation now where we have three separate distributions, and we need to be very, very clear on the terms that stand for the characteristics of those three different distributions. So we're going to revisit this idea of the words that do the work and take a look at some of the terms that you need to become familiar with. All right, so we'll start off with the first term, which is X bar. So X bar, I will refer to it a few more times probably as X bar just to illustrate it and where it is, but this is the sample mean. So when you see X bar, think of the sample mean, say to yourself, sample mean, and once you do that, we know exactly what it is. We know that we took a sample, we measured some characteristic for the individuals in that sample. They all got scores. We took the mean of that score. That's the sample mean. So we have X bar, the sample mean. We have N, which is the size of the sample. So this one's pretty straightforward. The size of the sample gets the symbol N, and that's just how big is your sample. Do you have 30 people in your sample? Then your N equals 30. You have 42 people in your sample, N equals 42. Did you do the NatSal census of Great Britain? Your N might be 200,000, right? It's how big is your sample size. And then we start getting into the Greek letters. And one thing that you'll notice is that oftentimes in statistics, this is a little shortcut to kind of help you remember some of these things. If you're dealing with a sample, you get English letters. If you're dealing with a population, you get Greek letters. So the mean of the population is going to have the symbol mu. So mu for the population mean. We got sigma for the population standard deviation. And then we have two new ones, which are mu x bar. And this is the mean of the sampling distribution. And I'm going to illustrate exactly what this is, but just know that that mu symbol with the subscript x bar, that is the mean of the sampling distribution. And then likewise, sigma x bar, that is the standard deviation of the sampling distribution. So this is a good time to start off on the Do It With Me demos. So we're going to go now to the Staplet. That is the Simulating Sampling Distributions Staplet. So if you haven't opened that up yet, I encourage you to open it up so that you can do this along with me. And what this is going to do is it's going to illustrate, first off, we're going to use it to illustrate these terms. And then we're going to use it to illustrate the relationship between the three distributions. So right now we only have one distribution up there. So what we're going to do to start this Do It With Me demo is up here where it says population distribution is, just to make it very, very clear, the difference between the population distribution and the distribution of sample means or the sampling distribution, we're going to take this and we're going to choose not normal, but we're going to choose a skewed distribution. So we're going to change our population distribution to a skewed distribution. And then the first terms that we're going to take a look at are down here. And we see that in this population here, we have a population mean of 3. So if we took all the members of this population, added them all up and divided by the size of the population, we would get a mean of 3. So that's a value right there. And then our population standard deviation equals 2.449. So there's your mu equals population mean. And there is your standard deviation, population standard deviation, sigma equals 2.449. So typically, when you're doing inferential statistics, you want to try to find out, for example, what the mean of the population is. And typically, we can never measure the actual population. We have to rely on samples to estimate what it is we want to know about the population. So in this case, we might want to take a sample to estimate, if this was unknown to us, to estimate what is the mean of this particular population. And also remember that with this simulation, we are getting a very specialized, omniscient view of the world. because typically you would not know the distribution of the population. Typically in the real world, this whole area here would be blank. You wouldn't be staring at this skewed distribution. So this is a very special case that we're using just for educational and demonstration purposes. So just bear that in mind. We typically don't know what the population is. All right, so now we're going to start sampling. And we're going to ask them to show a distribution of one random sample of size n equals, and we're going to change this to 10. Just because we want to deal in this first go through with a sample size where we can see the individuals, right? So we're just going to use a sample size of 10, and then we're going to select sample. And then what it does is it creates a second distribution here. And this distribution here, this is your sample data. This is your sample distribution. So this is a dot plot in this case. And every single one of these dots is a individual, is a person that you took directly from this population here. So you can see that this goes from 0 to 16. Your sample distribution goes from 0 to 16, so it's lined up. So this individual here, this 0.163, they came from right here in this 0.163 column of the distribution. This individual here, 2.343, they came from right here in the 2.343 column of this distribution. This individual, 7.297, they came from right here, 7.297. So these are 10 individuals that were grabbed from the population in our simple random sample. So we can see their distribution here, and not surprisingly, most of the sample comes from where most of the population is in this density curve. Very fewer came from the lower, less frequent portions of this density curve. And then importantly, we now have a sample mean. So we now have our X bar, that is our sample mean. Scroll up just a little bit. And that is typically our estimate of what the population mean is. So you can see that in this case, we got incredibly close. We actually kind of got lucky on this first one. So we would estimate that the population mean in this case is 2.988, when in reality it's actually 3. That's known, that difference is known as your sampling error. And in this case, we actually came very, very close. All right, everybody good so far? Okay, so I mentioned that there was a third distribution, and if we scroll down now, we'll see that third distribution. And what this one is this is a sampling distribution. And what the sampling distribution is it is a distribution that is not made up of individuals, it's made up of sample means. So it's not individual people from the population, it's a group of people, a sample, you take their mean, and they get 1 dot on this sampling distribution here. So all of the scores from these 10 individuals that made up our first sample gave us a mean of 2.988, and then that mean gets placed here on this sampling distribution at 2.988. So those 10 individuals in their population got chosen, became a sample, and then that sample gets a mean calculated, and that becomes 1 dot on this sampling distribution. So far, so good? Okay, so we're gonna scroll back up here to where we have our sample show distribution of sample size n, and we're going to quickly select one more sample. We just wanna add one more sample, take one more sample. And this is just simulating the idea of our ability to take an infinite number of samples and see what happens. Typically, you take one sample in the real world and that's it. You've done your experiment, you go on. But let's say that we didn't have to do that. And we can actually take another sample and take another sample. So we're gonna quickly select, we're gonna keep this at 1. We select one more sample, so we hit that. And you can see that our sample distribution here has changed. We're still pulling from the same population. Population has not changed at all. But now the dots here have changed, and we have 10 new individuals right? These are 10 new individuals that we pulled from the population, and they also have a sample mean. And in this case, our sample mean has now overestimated our population mean, and it's overestimated it by a fair bit, right? By about 0.46. So in this case, we have a sample that went a little higher than our sample mean. In this case, we overestimated our sample mean, our population mean. But notice that, again, we've taken this sample, and now that we have this new sample mean gets added here to our sampling distribution. So now we have two means in our sampling distribution. All right, so we're going to do it again. Let's try it for a third time. We select a new sample. This third sample, wow, this is as skewed as I've ever seen it. So this third sample here, again, these all come from this population here. I know this one up here doesn't look like it comes from this population, but that's because this line got so thin. So this is actually a pretty momentous occasion, because just kind of estimating how rare this dot would be, I would say that's probably like 1 in 20,000. So you are here live when a 1 in 20,000 sample has occurred. But importantly, these are 10 new individuals from this population, and they have their own distribution, right? They have a distribution that is heavily skewed over here to the right. This sample now has a new sample mean. This sample mean vastly overestimated what the population mean is, but importantly, this new sample with its new sample mean gets added to the sampling distribution. And we now have it registered here as a dot at 5.353. So is it clear the relation between the population, the sample, and the sampling distribution? Does that make sense so far? Okay. So what we can do now is let's do this manually a few more times just so we can kind of see this getting built up. But we can select another sample, and we get a new sample here. And that new sample and its new sample mean, that mean gets added to the sampling distribution. So there it is right there. And then we can select a new sample, and we can select a new sample, and over and over and over again, we have our sample being chosen from the population, and then that sample mean gets added to the sampling distribution. And one thing that we'll notice when we take a look at this sample mean here is that sometimes, if you recall last time we met, I mentioned that the sample mean is an unbiased estimator of the population mean. And the reason for that is that sometimes it overestimates the population mean. Population mean is 3. Sample mean is 3.12. That's an overestimation. Sometimes it underestimates it. Sample mean in this case for this new sample is 2.68. So it will sometimes overestimate, sometimes underestimate, underestimate, way underestimate, overestimate, overestimate, underestimate. But the point is that it's an unbiased estimator of that population mean. Okay, so we've now built up our sampling distribution. And the sampling distribution, now that we have, well, let's select a few more samples. So now that we have a few more samples in this, we have a sampling distribution here. And notice that it also has a mean, and it also has a standard deviation. So this sampling distribution comes with its own mean. Mean is 2.965 at this point, so right about there. And it's got its own standard deviation. And what we're going to do now to just sort of fast forward things is let's quickly select, and instead of just one, let's quickly select 1,000 samples. So this is going to speed run us through 1,000 samples selected from this population. It's going to build up this sampling distribution by adding 1,000 samples. So we got that 1,000 set in there. We're going to hit select samples, and it'll immediately add 1,000 right now. Okay, so now we have ourselves a distribution of sample means of 1,000 samples randomly taken from this population up here. And the two important things to notice is that this mean here for the distribution of sample means, or this sampling distribution, this mean is 2.989, and that is incredibly close to the population mean of 3. So that's the first thing we'll notice. And then the second thing you'll notice is that the shape of this sampling distribution does not look at all like the shape of the population. So I'll zoom out of this a little bit so we can get them both on the same screen. But you'll notice that the population distribution is heavily skewed right. So we have a very long tail to the right. And yet the sampling distribution does have a little bit of that tail going on here, but it's much more symmetrical, much more bell-shaped. This is much more, dare I say it, normal in its distribution than this skewed distribution over here. All right, so that is our first look at the sampling distribution. Any questions so far on what we just saw? Okay, so now let's go back and we'll take a look at some of the stuff that we just discovered. So we've illustrated some of the words that do the work. So you now know what each of those refers to in terms of that application that we just explored. And now we're going to take a look at what is the relation of each of these things to the population distribution. Because again, our interest is in this distribution here. This is the distribution, that population distribution. This is what we really want to know. But unfortunately, this is almost always a mystery to us. So what we can have access to is we can have access to the sample, and then that gives us a way of trying to figure out what is this population distribution. So what is the relation between the sample mean and the population mean? Well, as we just saw, that sample mean is what's known as an unbiased estimator of the population mean. Because sometimes the sample mean is overestimating what the population mean is, sometimes it's underestimating what the population mean is, but in general, it's not biased in either direction. So it's an unbiased estimator of what the population mean is. What about the mean of the sampling distribution? What is its relation to the population distribution? Well, the mean of the sampling distribution is actually exactly equal to the population mean. So if we were to run this and do a whole bunch of quickly selecting samples from this, let's say that we add another 10,000 to this and hit select samples, you'll see that the mean of this sampling distribution is now incredibly close to the mean of the population distribution. The mean of this sampling distribution is now 3.012, and it's incredibly close to the mean of the population distribution. And the reason that it equals a population distribution is that this is made up of samples. So each of these little dots, I know we kind of lost the dots. Each of these little dots, let's get it back to where we can see some dots. There we go. Each of these little dots is a sample. And because the sample is an unbiased estimator of the population mean, some of these dots are going to be underestimating what the population mean is. Some of the dots are going to be overestimating what the population mean is. Half of them are going to be overestimating. Half of them are going to be underestimating. When you take the mean of all of the sample means, you're going to end up with a mean that is exactly the same as your population mean. So in this case, we're just by chance even closer, 3.007. The mean of the sampling distribution equals your population mean. So that is a very important relation between the two, and one that we're going to exploit later when we do inferential statistics. All right. Standard deviation of the sampling distribution. what is the standard deviation of that sampling distribution and how is it related to the population standard deviation? Well, luckily they are related, but this time it's not as simple as being equal to each other. So the standard deviation of the sampling distribution is not equal to the population standard deviation, but it is related to that population standard deviation via the size of the sample. So the size of the sample controls how related how the standard deviation of the sampling distribution is related to the population standard deviation. And the relationship is this formula right here. So we have in this formula standard deviation of the sampling distribution, standard deviation of the sampling distribution equals the standard deviation of the population divided by the square root of the size of the sample. And that sample size is what determines that relationship. So one of the things that this does, and we'll go back to our demonstration here. One of the things that this does, and let's add some more, we'll add another 3,000. All right, that'll do. So one of the things that this does is it, first off, lets us relate the standard deviation of the sampling distribution to the standard deviation of the population. But you'll notice that in the formula, we are dividing by the square root of the size of the sample. Now, the fact that it's a square root, that's just how the math shook out. But importantly, especially for when you're doing work in psychology, what this means is that the bigger your sample is, the smaller the variation in your distribution of sampling means, the smaller the standard deviation of that sampling distribution. So the larger your sample size, the more tight and less variable your sampling distribution is. So let's take a look. Now we'll run a few scenarios on this. So we did this with a sample size of 10. And this value right here, 2.499, if we took that and divided it by the square root of 10, we would get something very close to 0.783. Again, it's close because this is a simulation. If we could do this for 1 million samples, it would be exact. But that's the relation between the two. So what this has in effect done is it has decreased our variability that we're dealing with from 2.449. It has decreased it by more than a factor of 3 to 0.783. And less variability means more power to notice differences, right? Less variability means that small differences will stand out more. It means that you can detect whether a treatment works. Even if the treatment is not as powerful, you can detect whether an intervention works without a large without a large effect size. Basically, if something exists and you're looking for it, the smaller your variability, the more likely it is that you will find it if it's out there. So we have here a standard deviation of 0.783. That was for this sampling distribution when we did a whole bunch of samples of size 10. Let's take a look at what happens now when we do sample sizes of 20. So we're going to enter in 20 here, and we have 0.783. I'm going to write that down because there's no way I'm going to remember all these numbers. All right, we have a standard deviation of the sampling distribution of 0.783 when our sample size is 10. All right, we are now going to increase our sample size to 20. And we're going to select 3,000 samples. So we go back here, we set our sample size to 20. We go back here, we hit select samples. And now we have a new distribution. Notice that the shape of our sampling distribution here, now that we've chosen 3,000 new samples and these samples were of size 20, notice that the shape really hasn't changed. It's still pretty much that bell curve normal shape. Notice that the mean has not changed either. The mean is still equal to the population mean. that population mean of 3. But do notice that now the standard deviation has gotten a lot smaller. It used to be 0.783. But now that we have 20 subjects, it's gone down to 0.558 with a sample size of 20. And let's just do it one more time. And we're going to go up here and we are going to change this from a sample size of 20. And let's say that we got ourselves a big grant and we're able to run 200 people in our study. So we have a sample size of 200 now. Now we're going to select these samples. And now we have an extremely tight sampling distribution. Same mean. The mean has not changed because the mean of your sampling distribution equals the mean of your population. However, now that standard deviation has gone down to 0.174. So when we had a sample size of 200, we got that variability, that standard deviation of the sampling distribution down to 0.174. And the bottom line is that the smaller your standard deviation, the more powerful your study is. The smaller your standard deviation, the more likely you are to detect a difference if the difference exists. So having 200 subjects and a standard deviation of 0.174, that's like having access to an electron microscope. Whereas when we only had 10 subjects and we had that standard deviation of 0.7, now it's 0.766, that's like looking through a high school microscope, right? It's still going to get you some results, but it's just not as powerful as it is if you have a larger sample. And the power of that larger sample comes from this relation here, because you're dividing that population standard deviation by the square root of the size of your sample. The bigger you have this, the smaller the standard deviation of the sampling distribution is going to be. All right, any questions on that and the relations between them? All right. So the last thing that we're going to dive in deep today is the actual shape of the sampling distribution of a sample mean. And for this, we're going to introduce a very, very important concept, which is known as the Central Limit Theorem. And what the Central Limit Theorem says is that if you select a simple random sample of size n from any population, and that population has a mean of mu and a standard deviation of sigma, that Central Limit Theorem says that when your sample size n is sufficiently large, the sampling distribution of the sample mean, x bar, is approximately normal. So we're going to break this down as we go back and see this in a simulation. Alrighty, I'm a little excited about sampling distributions, clearly. But anyways, the important things to realize here is that this works, and I can't stress how important this is. This works for any population. Any population. It doesn't matter if it's been a population that's been with us forever and we have tons of data on them. It doesn't matter if it's a population that popped up last year. This is the reason why when social media exploded a couple of decades ago, psychology could ask questions about, well, what is the effect of social media on the population of people using social media, even though, things like Facebook and MySpace did not exist prior to that. Well, we can do it because of the Central Limit Theorem, which says this works for any population. So anything that you're interested in, no matter how finely defined or no matter how new it is, you can do psychology studies on it because this will work for any population. And the other thing that it tells us is that not only does this work for any population, but as soon as you take a sample from that population, you are dealing with a sampling distribution that is approximately normal. So the sampling distribution will be approximately normal, and we will know things about that sampling distribution because it's related to the population by the mean mu, the sampling distribution has the same mean, and the standard deviation, the sampling distribution has a standard deviation of the sigma of the population, standard deviation of the population divided by the square root of the size of the sample. Most important things, though, to take from that, any population, take a sample, and you're dealing with a situation that's approximately normal. So let's take a look at that. So we've already seen it here with this skewed distribution here. So the first thing that I want to show you is why we do samples at all. So to show you why we need to use samples in this and why we're not just doing case studies, we're going to go up here and we're going to take this sample size of 10 and we're going to change it to a sample size of 1. Okay, so we now have a sample size of 1, and there we have our single sample of a single person, single individual, and this individual has a score of 2.48, and they have a mean of 2.48, not surprisingly. And let's say that we did that for 3,000 random samples. Has it already? Oh, it hasn't done it yet. Okay, so we'll build this up piece by piece. You have our skewed population distribution, which we don't know. We're not sure about what it is. We have a sample of a single individual, a case study taken from this population. And we have our sampling distribution now, which is the mean of the sample that we took, 2.48. And if we, again, we'll keep it at 1 for a little bit. If we just do this again and again and again and again, then we are adding this individual that came from the population, we are adding him to this sampling distribution, which are samples of the size of 1. And if you were to keep doing this over and over and over again, what you would find, and we're just going to speed run this, let's put in 10,000 to make it abundantly clear. If you were to select now 10,000 samples and take a look at this, the shape of your sampling distribution, you would find it looks like this. And what you find is that your sampling distribution for a sample size of 1, got to zoom out one last time. You take a sample size of 1 and your sampling distribution has the same shape as your population. That's because your sampling distribution here is made up of individuals. These are sample sizes of 1. These are individuals. These are individuals. That's why the two shapes are exactly the same. And if we were going to add, let's say another, we do 50. Oh, okay, we're losing resolution there. Not going to work too well on that. But anyways, the more we simulate this, the more closely our sampling distribution is going to look like our population. And that is bad. That is not good because we don't know what the population looks like. So if we're dealing with a sampling distribution that looks like our population, that's not going to help us at all because we have no idea what our population actually looks like. So that is why typically psychologists will not do studies with a subject size of 1. And if you do see a study with a subject size of 1, typically they're a case study. And usually they're only on subjects that are somehow so extraordinary that you can't wait around for a sample. So studies like the individual S who had perfect memory for their entire life, you can't wait for 20, 30, 40 people like them to show up. So if you're dealing with people with extreme abilities or extreme scores in the distribution, sometimes you have to do a case study. I'm not here to knock on case studies. I love case studies. They're some of the greatest leaps in psychology have come from case studies. But importantly, you can't do the statistics we're going to be doing in inferential statistics with case studies. It's just not available because we don't know what this population distribution is. And if you're dealing with case studies, you're dealing with a sampling distribution that looks exactly like your population distribution. All right, but if we start adding samples, and let's take this out of the 50,000. Let's go back to 1,000. I think that's a good. That's a good size for it. Okay, so if we start doing samples and we have a sample size, again, let's do 10. So we put in our sample size of 10 and we select 1,000 samples and we're going to see what our sampling distribution looks like. We select those 1,000 samples and you can see that our curve is approximately normal. It's symmetrical, it has a single peak, it's symmetrical on both sides. So we are approaching what is looking like a normal curve. And if we increase the size of our sample, let's say that we go from 10 to 30, and now we select our samples again, we can see that it's even more like a normal curve, and I'll just kind of show the corresponding normal curve to sort of outline how normal we're getting. So we have a distribution that is approximating that normal curve, and the higher this goes, so we have a sample size of 100, the higher your sample size, the more like a normal curve your sampling distribution becomes. And importantly, it becomes like a normal curve regardless of what your population looks like. So we've been dealing with this skewed population for a little bit right now, so we're going to switch it up. So instead of skewed, we're now going to try a uniform population. So on your population distribution we're just going to choose uniform. And I think I messed it up. We're just going to choose uniform. So now we have a uniform population distribution. And what that means is that out of those 10 scores, every score is equally likely, right? This is something where there are no extreme scores in this case. There are no rare scores. All the scores are equally distributed across the entire population. So here we have a mean of 5. We have a standard deviation of 2.87. And if we select a single sample, we'll start it off at, let's start it off at 10 again. We'll just select a sample. So again, we take 10 individuals from the population, and those 10 individuals and their mean get placed here in this sampling distribution. And as we continue to select more and more samples, we continue to build up our sampling distribution. And if we fast forward to 1,000 samples and we select those samples that show that corresponding normal curve, we are getting a sampling distribution that is looking very much like a normal curve. And this sampling distribution came from this population, this assuredly not normally distributed population. But importantly, it's turning into a normally distributed population. And the higher the size of your sample, the more closely, two things are going to happen. The higher the size of your sample, the less spread your sampling distribution is going to have. And also the more closely it's going to be fit to this normally distributed curve here. So your sampling distribution becomes a normal distribution when your sample size is sufficiently large. And typically for most populations, a sample size of 30 is sufficient to do this. So let's keep going. Let's see if we can actually find something that doesn't work. Let's try the bimodal. All right, so we have bimodal here. And one thing I didn't know about bimodal, and this I kind of discovered, and I'll show you this real quick just to kind of illustrate that these are two different distributions. And I will just give you a spoiler alert. When students start inferential statistics, the biggest error that impedes their progress is confusing the population distribution with the distribution of sample means. And those two things are two completely different entities. So one thing that kind of surprised me on the bimodal distribution is I was playing around with this earlier and I decided to see, well, what about the smallest possible sample that's still a sample size of 2? What does that look like? So if you select a sample for a sample size of 2, and then let's quickly build up our sampling distribution with 1,000 random samples, and we'll select those samples here. you get this really weird trimodal distribution. So if we add a few more, let's go to 10,000. You can see it's kind of, I don't understand why this would happen. We're taking samples from a bimodal distribution, and somehow the part of the population that is one of the least represented parts, that low dip in that distribution, is actually one of the most represented parts in the distribution of sampling means. So this kind of surprised me. Hopefully this will help you remember that your sampling distribution, your distribution of the means of the samples that you've taken, is a completely different thing than your population distribution. All right, so let's not mess around with this. Let's try a sample size of 30 for our bimodal distribution here, our bimodal population. So if we're having a sample size of 30 and we select ourselves, let's go with those 1,000 samples. Again, here you can see, and I'll show the corresponding normal curve, this sampling distribution is starting to approximate that normal curve. And if we were to add, I like to use 1,000 because you can kind of still see the dots. But if we added 10,000, you can see with these lines, or maybe you can't, I don't know how good the resolution is, but these lines basically match up perfectly with that normal curve. So as long as you have a sample size, and again, typically the rule of thumb is that if it's beyond 30, regardless of the shape of your population distribution, you're safe, your sampling distribution will be normal. But as long as you have that sample, you will be dealing with a normal distribution. And the reason that that's important, let's get back to something that's a little bit easier to see. The reason that that's important is because when we start hypothesis testing, we are going to use our sample mean. And we're going to need to compare it to something. Basically, all that inferential statistics is and all that hypothesis testing is asking yourself, how weird is this sample? How unlikely is this sample? How much of a fluke was this sample mean? And because we cannot compare it to this population over here, because we don't know what the population is, we wouldn't be able to answer that question unless we had that mathe-magic of the sampling distribution being normal, because we can now use all of our normal skills and say, all right, this sample here is 15.459. Our sampling distribution has a mean of 15 and a standard deviation of 0.967. Well, now I can go here and I can calculate an area under the curve, and that's 15.001, and that is 0.967. And I can plot my distribution, and I can say, well, how unlikely was this? Values to the right of a value, 15.495 for the population, sorry, for the sample mean, calculate that area. And now I know that this sample mean, getting something that high or higher, you have a probability of 30%. It's not that unlikely. Importantly, though, I can do that because this sample, even though it came from this non-normally distributed population, this sample now belongs to this normally distributed sampling distribution, this normally distributed distribution of sample means, and that's why we can start doing stats with these tools. All right, so let's run the gamut here. We did the bimodal, we did the uniform, we did the skewed. We'll save the normal one for the end. This actually is so powerful. It even works with categorical data. It even works with data where it's either yes or no, success or failure, this way or that way, right or left. You can even use it with categorical data, because as long as you select 30 people from this population where success is equal in chance to failure, for example, if we select that sample and then we generate the sampling distribution, even with something that is categorical, where it's either or, this sampling distribution is looking like a normal curve. So this is what gives us the power, because it doesn't matter in psychology to do the work that we need to do, because it doesn't matter if it's uniform, it doesn't matter if your population is skewed, it doesn't matter if it's bimodal, it doesn't matter if it's categorical. Every once in a while you come across a normal population. It doesn't even matter if it's normal. It might, I mean, regardless of what your population looks like, this occurs over and over and over and over again. And it's that little bit of mathe-magic that occurs when you're dealing with samples, because that opens the door to the central limit theorem. The last thing that I'll mention before we leave the idea of simulating sampling distributions is that one of the things that trips up students the most, I alluded to this before, I'll mention it again. One of the things that trips up students the most is they get the population distribution confused with the sampling distribution. And one of the reasons that this happens is because oftentimes when textbooks and instructors introduce the idea of the sampling distribution, they'll start with a normally distributed population, because a normally distributed population is what we've been working with so far. So all those examples that we had about the school psychologist going to the superintendents, helping out the gifted program, helping out the mental health programs, we started off with, well, let's say that the population is normally distributed. So oftentimes they'll say, okay, well, let's keep going with that. We have a normally distributed population, and we take our samples and we build up our sampling distribution, and lo and behold, our sampling distribution is also normal. I found that can get confusing. So what I would highly, highly recommend is, before you dive into doing any work with this, before you dive into doing any homework, go to this simulating sampling distributions and try some of the non-normally distributed populations and just play around and see what does a sampling distribution of sample size 2 look like, right? And it's kind of spread out there. Well, what about a sampling size of 12? What does 12 look like? Oh, okay, 12 is starting to look, a lot normal. I would highly recommend that, because what that will do, if you just play around with it for a little bit, it will help you remember that this does not equal this, because visually, this is very apparent that this sampling distribution does not equal this population distribution. It is very visually apparent that this sampling distribution does not equal this population distribution. And the more you do that, and the more you kind of simulate and work with populations that are not normally distributed and see that they generate sampling distributions that are normally distributed, it'll help separate those two concepts in your mind so that you don't make that mistake. Because the number one mistake that occurs in inferential statistics, when students are learning inferential statistics, is they will take a sample mean and we'll ask the question, how unlikely or how weird is that sample mean? And because they're so used to using the population distribution, they'll take that sample mean and they'll compare it to the population distribution. And that's wrong. What you need to do is you need to take the sample mean and compare it to the distribution of sample means. And when this one is normal, because it always is, and your population distribution is not, you're much less likely to get those confused. And you'll say, well, I can't use this, so I got to use this. And it will reinforce that idea that you compare sample means to the distribution of sample means. And that population, even if they give you the information, because sometimes those textbook questions are a little tricky, even if they give you the information, just know that it's this sampling distribution that you're working with. And the more you kind of play around with these population distributions that don't look like normal distributions and see that they come up with that normally distributed sampling distribution, the less likely you are to take that sample mean and compare it to the wrong distribution, which is the population distribution, and you compare it to the right distribution, that distribution of sample means. All right, that was my final PSA for the sampling distributions. Any questions on what we covered today in that distribution of sample means? All right. So the last thing that we're going to do today is a short little teaser for what is coming up. So we have now built the last tools that we need and the last big concepts that we need in order to start hypothesis testing. And hypothesis testing is exactly what it says on the tin. It's when you start testing hypotheses. So I have a new treatment for depression. Does this treatment work, right? I want to test out hypothesis. I have a theory about how visual metaphors are processed in the mind. I run an experiment. Did my experiment, confirm my theory? That's hypothesis testing. And usually when we talk about hypothesis testing, or when we talk about what we're looking for in psychology, is we want to know, did this treatment work? Did this effect make a difference? Does this way that we think change, our behaviors? We want to know if something happened. That's usually what psychology is looking for. And what you're going to run into, and sometimes this confuses students, is that inferential statistics is built around what if nothing happens? So you're going to come across what's known as a null hypothesis. And it can be a little confusing because our minds are so intuitively set up to detect whether things happen. And then we come across a statistical system that says, well, we're going to try to answer these hypotheses questions by detecting whether nothing happened. And sometimes that doesn't make sense. So we're going to explain it when we get there, but I just wanted to put a little teaser out there for you to kind of get it into your mind, get it into your subconscious, and maybe when we hit this in a couple of weeks, it'll make massive sense. So I'm going to give you two scenarios. I said we were going to talk about cars and boyfriends. Let's start talking about boyfriends. So let's say that you have a friend, and this friend has been single for a while. And then you see them after a little while, and they come up to you and they say, hey, I just met somebody, and I have a boyfriend now. I'm in a relationship. And you're like, well, great, that's wonderful. And they ask you, what do you think he looks like? And you're sitting there and you're like, well, what does he look like? And you think about it for a minute and you say to yourself, I have no idea what a boyfriend looks like, right? Because when your friend says, hey, I have a new boyfriend, what do they look like? You start thinking to yourself, all right, well, they might look like this, right? That's one possibility. Maybe that's what their boyfriend looks like. Or they might look like this. Maybe that's what their boyfriend looks like. Or they might look like this. Or they might look like this. Or they might even look like this, right? There's a lot of possibilities for what a boyfriend could look like. But if your friend came up to you and said, hey, I haven't seen you in a while, this would be a weird conversation to just throw out there. But if they came up to you and said, hey, I haven't seen you in a while, I have no boyfriend. And if you thought to yourself, well, wait a second, what does no boyfriend look like? You know exactly what no boyfriend looks like. No boyfriend looks like this. That's no boyfriend. They're not there. So we don't have any idea what boyfriend looks like, but we have exactly the right idea of what no boyfriend looks like. So that's the boyfriend's example. We're going to drive it home. We're going to drive it home with the cars example here. Let's say that that same friend came up to you and said, you know what? I just bought myself a new car. I went out there and I got myself a new car. What do you think it looks like? And again, you're faced with a conundrum. And you're like, well, you got yourself a new car, probably new used car, because we don't want to be too extravagant. But you got yourself a new car. Maybe it's this. Maybe it's a 2012 Toyota Camry. Possibly. It could be a Honda Civic. Possibly. It could be a Toyota Corolla. Those are actually the three best guesses because those are the three most common cars on the road. But at the same time, it could be a Subaru Outback. It could be a Ferrari F80, right? These are all cars. These are all possibilities. We don't know, and we have no way of knowing what car looks like before we see it. We don't know what car is. But if your friend said, hey, you know what? I have no car, then you would say, hey, I know exactly what that looks like. That looks like this. So this is no car standing next to no boyfriend, and we know what that looks like. So let this just kind of sink in a little bit. That's all I wanted to say about it. And then when we come to the null hypothesis, when we come to hypothesis testing, we get to the null hypothesis. Remember the cars, remember the boyfriends, and hopefully why we deal with null hypotheses will make way more sense, and it'll seem more intuitive than it typically does, which is massively counterintuitive. All right. Any other questions or anything that we've covered today? All right. Well, that worked out rather well because that's all that I wanted to cover for today. So again, highly recommend go to that Statlet, just mess around with it, put in some weird sampling sizes, try the weird distributions, build them up one at a time so you can actually see that sampling distribution grow, and just get very familiar with it, and just know that your population distribution is one distribution. Usually we have no idea what it is. Your sample comes from the population. Sample is what we can measure, and that sample belongs to a sampling distribution, and we know what that sampling distribution is, and it's normally shaped with the same mean and a related standard deviation to the population distribution. And the last thing that I'll leave you with is teaser number 2. So I just said that we're going to use that sampling distribution. And we know what that sampling distribution is because it has the same shape of a normal distribution, and it has the same mean as the population and the standard deviation that's related to the population distribution. And you might be sitting there thinking to yourself, well, wait a second, how useful is that? You just told us that we don't know anything about the population. So we know that the sampling distribution is normally distributed, but we don't know what the population mean is. So how do we know what the mean of the sampling distribution is? And we don't know what the population standard deviation is. So how can we figure out what the standard deviation of the sampling distribution is? And all of that and more will be answered. There is a way around it, and we'll show you that. But just in case that was something that was hanging you up, know that there is a way forward. But other than that, I think that's enough. I think that's a lot. Let it all sink in, and I will see you all next time.